Okay, we're going to do two major applications. The first one is the application for differential equations. It's literally the primary reason why this class is a prerequisite for DiffEq, because of one type of problem. Now, when I teach differential equations, I do this in DiffEq, and it's the last two lectures of DiffEq. So I do the stuff we're going to do in the last two lectures so that if a student is concurrently enrolled in linear, hopefully they will have seen it in linear first. I mean, think about that logically. You want to see your calculus in calculus before you see it in physics. You want to see your logarithms in math before you see them in chemistry. So you want to see the eigenvalue, eigenvector problem you're going to do in differential equations here first so you know how to do it. I've had many, many students over the years who were dual enrolled, and they did this problem early on in the DiffEq course. Were completely blown away because there was only one other professor in the 37 years I've been here. Yeah, I had to think about that. Only one other professor who actually taught differential equations and linear algebra, the late Mr. Brage. He died many, many years ago. Meaning every person who had ever taught differential equations had no experience whatsoever in linear algebra, and they're teaching you how to do the highest level thing in linear quickly in DiffEq, without any understanding or comprehension or any skill with working with a matrix. That to me is kind of scary, but you don't need linear algebra in order to do DiffEq in general. You do it for this problem. So here's what we're going to look at. Let's see, do I want to use dt? Hold on a second. Yeah, I'm going to use t's. The y's are functions. They can be polynomials, they can be transcendental functions, they can be anything. Okay? But for what we're doing, okay, basically, well, they can be anything, but we're going to see there's only some kinds of things they can really end up being. So I have a system of first-order linear differential equations. And those terms are really, really important in that that's the only problem we can solve. First order simply means they're all first derivatives. Linear, because they're just y1 times coefficients. There's no y1 to a power. There's no function of y1. Okay? So this is the friendliest kind of system of differential equations to solve, but this is something that is not trivial right now, and we couldn't guess at an answer right now, even if we had all the coefficients. So I'm going to get in the Wayback Machine, and I'm going to remind you of something that you learned a long time ago in calculus. Okay? Population growth. So in my calculus class, this would be day 2 of the semester in Calc 2. I want to solve the following differential equation. This is the uniform, universal population growth problem. The rate of change, if y is population and t is time, the rate of change of growth of a population is always a constant times population. I would say think of it in terms of money. So I said, oh, I found this great account, Stephen. If you put your money in this account, you'll get $100 interest every month. Does that even make sense? I didn't tell you how much you had to put in. Oh, so put in $1. Does it work that way with interest that you get a fixed dollar amount? No, you get a percentage of what you put in. Populations grow or decay based on how many there are. You don't say a population grows by this many people per year. That doesn't make any sense whatsoever. I have a town with 2 people. Population grows 10,000 people per year. No, population can only grow as a percentage of how many people are currently there. So K is the growth rate. In words, we say percentage, but it would obviously be a decimal. And Y is the population. So if the population were growing 3% per year, then we'd say dy dt is 0.03 times Y, the rate of growth. Now, does this also work for decay? Yes, if K is negative, then it's decaying. Things that die are decaying, things that are alive typically are growing. I need to solve this problem. Now again, this is the beginning of Calc 2. So what we do is we say, well, we can treat it as a separable differential equation. That's absolutely correct. Or we can use the Calc 1 approach, and that is I'm going to integrate both sides, but not yet. I need to move the y over. So 1 over y dy dt equals k, and now I'm going to integrate both sides with respect to t. I don't need you to remember how to integrate. I need you to get to the result. Okay? So if I do this, that is the same as this. This goes back to your u substitution. Remember when you substituted du dx integrated with respect to x, you got an integral du. Because there are actually no t's in this statement, there are only y's. So dy dt integrated with respect to t is dy. And on the right side I have still at that because I'm still integrating with respect to t. Now if I had treated this as a separable differential equation in the beginning, this is what I would have gotten. You do separable differential equations also in Calc 2, but most people don't remember them because it was a very high-level problem at the beginning of Calc 2. This is something that's a daily thing in a DiffyQ class. But now when I integrate this, I get log y equals kt plus c1. Now, y is population, so it can't be negative. So when I exponentiate both sides, I get y as e to the kt plus c1, which is e to the kt times e to the c1, so we just write it as c2 e to the kt. So the solution to this differential equation is y equals c2 equal. But if I want to get a little more specific, what is y at time 0, which we generally in math and science put a subscript of 0, that just means at time 0, is what? c2 e to the 0. Oh, so c2 actually isn't an arbitrary constant at all, is it? It's actually the initial population. So the solution, not a solution. I'll write it this way. Y of t equals y0 e to the kt. The solution to any differential equation of this form, which is the universal population growth or decay problem, is this. So if k were negative, then I would be decreasing exponentially. If k is positive, I'm increasing. So why am I showing you that? That means every one of these y's is going to be an e to the something. Now, here's the what if. What if any of those coefficients are complex? Well, I'm not doing that problem this semester, unfortunately, but I'll give you a hint. That's where sines and cosines come from. Every problem that exists, if you have an exponential function, you are dealing with a purely real set of functions. Any problem that you've ever done in your life where sine and cosine appear means you were dealing with purely imaginary things. You didn't know that. And any problem that has e's and sines and cosines simultaneously, then you were dealing with complex numbers that have both real and imaginary. That's a very simple proof. It would take me a minute to prove in a DiffyQ class. Did you know that? Real numbers show up because you got e to the something. Complex numbers show up because you get sines and cosines. Sines and cosines can only show up when there's complex, or excuse me, purely imaginary. Isn't that crazy? Whoa, never saw it coming. That goes back to when I set up the hyperbolic functions. I'm going to do a little bit of that next day, by the way, to show you where they come from. So when you did De Moivre's theorem and pre-calculus and you did other things, that's where some of this stuff comes from. But this was important because at the end of the problem, when I get an answer and I'm solving a system of differential equations, I cannot solve this problem. But what if the problem were this instead? What if this was the only thing on the right side? What if all of the other coefficients were 0? Then can you tell me the solution to this? Yeah, you'd say it's c, what? E to the a11t. That is the solution. Now, short of giving you an initial condition, yeah, I wrote y0 over there, but I still don't know what y0 is. I'd have to tell you that. So leaving it as a c is fine. You don't need to call it y0. But does everyone understand that this is the solution to this? That's why I just did that. Problem is I have too many things here. I have a coefficient matrix. Wouldn't it be cool if I could come up with a matrix that was similar to that coefficient matrix that was, I don't know, diagonal? That is the entire problem. That is why this is considered the most important thing maybe going into a DiffyQ class. Because everything else in DiffyQ is really low-level calculus. When I mean low-level, I mean Calc 1 and Calc 2. There is no Calc 3 whatsoever in a differential equations class. In fact, it's the first 5 weeks of Calc 2 with some series. You do some series at the end, but it's not all that complicated. It's just messy. So what I want to do is rewrite this problem as a matrix product. So I've got dy1 dt down to dyn dt equals a11, I'm going to be lazy, a1n dot 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 an1 dot 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 ann. Okay. And then over here, y1, y2 dot 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 y1. So we already know we can do this. I cannot solve this though with an inverse. Because I have functions on the left, I have functions on the right. There are no constants anywhere. Okay, that's a big difference. When we did this problem at the beginning of the course, these were constants, weren't they? Then I could use the inverse matrix and life is good, but these are not constants, so that won't work. So we're going to rename our matrices. We're going to call this the y prime vector, just to make the notation easier. Capital A, and then we'll call this the y vector. There's no ambiguity. Now, just understand, most DiffyQ books, they'll just put primes on all of these, which makes me laugh. Because it's impossible to get a right answer at the end. Why is it impossible to get the right answer if I put primes instead of dy/dt's?
Might not be.
Because it's not possible to know what the independent variable is, and that's actually the most important part of the problem. If I said integrate over there, but I didn't tell you with respect to what variable, you couldn't answer the question. It's not possible to answer any question with primes, because prime is incorrect notation 100% of the time. A variable can't be prime, only a function. So if you wrote y1 prime of t, that would be acceptable. But if you just write y prime, there's no possibility you could know what the independent variable. And by the way, in real life, it's never x. Those who've had physics, you know this. In fact, you're more likely to have dx dt than even dy dt. It's just really bad math that all the DiffyQ books do the same bad math. They don't tell you what the independent variable is anywhere in the problem, and then they just randomly change them from one problem to the next. So one problem will be t, the next one will be an x, the next one will be q, and you're supposed to know. But that's really not good math, and you might have more than two variables also, because everything's going to be a composition of functions. So whether you write this or write this, I don't care. But include the t, otherwise your answer, you won't know that it's supposed to have t's. And it does look silly when you put functions of x when the problem is functions of t, because x will also be a function of t. Now, in order to solve this, my goal is to diagonalize matrix A. Because if I can diagonalize A, I might be able to get somewhere, but I can't see where it is now, so I'm going to walk you through. It's a little bit complicated, okay? So I'm going to walk you through the process. All right, now that I've called them this is the form. Now, here's what I want you to consider. A, first of all, has to be diagonalizable. If A cannot be diagonalized, this cannot be solved. It's that simple. That's why I said we're not messing around with things that can't be diagonalized. Being diagonalized means I have enough eigenvectors. If I cannot diagonalize this, I can't solve this. And the interesting thing is I have a really well-written differential equations book that does problems that can't be diagonalized, and they solve them anyway. The problem is the solutions are not correct. they kind of do a little hand-waving because it's like the author didn't realize if you can't diagonalize the matrix, you can't finish the problem. And there really is a unique solution at the end of this if I diagonalize. So what we're going to do is assume there's a p and a p inverse. Because I'm going to assume this is diagonalizable. I'm going to assume I just asked a question that can be answered. Because if it can't be, we'll know immediately. Right? The moment we can't come up with enough eigenvectors, and therefore there is no p and there's no p inverse, then there's no point in continuing that problem. So let's assume there's a p and a p inverse. So here's what I'm going to do. I'm going to let a new vector w equal p inverse times y. Again, assuming p and p inverse exist, can we all find p inverse? Absolutely. Assuming p and p inverse exist, we're going to find p and we're going to find p inverse. But before I find them, I'm going to let w equal this. Then what must y equal? PW, and that's the key. I don't start by saying let y equal PW, because what's W? I start by saying let W be P inverse Y, then automatically that statement is true. Then the y prime vector would have to equal P times the W prime vector. And I'm saying, so these would be whatever the y vector is, I'm going to multiply it by this. So then the w will clearly be a linear combination of the y's. Does everybody see that? I have an n by n matrix times an n by 1. So w1 will be a linear combination of y1 through yn, and w2 will be a different linear combination. It'll be one term, but it'll be a big old nasty linear combination. Now, what do we know about the derivative of a sum? It's the sum of the derivatives. Oh, so if this is a derivative vector and this is a linear combination of linear combination of these, then this is a linear combination of their derivatives because it's a derivative of a sum is the sum of the derivatives. I'm not making any great leaps of faith here. Again, this is a linear combination of the y1 through yn, so this is a linear combination of the derivatives of the y1 through yn. You with me? This is kind of a key step in the entire process. Now with that, then I have, let me rewrite this, so I have pw, that vector is equal to the y prime vector, but that's equal to a y. Okay, so now I have this statement here. But y is equal to pw. So this is now a pw. I've got pw prime is a pw. Anybody see anything that would be a really good idea to do about right now? Maybe multiply both sides on the left by p inverse. And if I multiply both sides on the left by p inverse, then I have the w prime vector is p inverse ap times the w vector. Well, why is that such a cool thing? Because that is a diagonal matrix. In fact, it's not only a diagonal matrix, what is it? A diagonal matrix of eigenvalues. So think of this now. This is now w1 prime of t down to wn prime of t. This is lambda 1 dot 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 down to lambda n. This is w1, w2. The w's are functions. These guys are functions. These guys are not vectors. This big thing is a vector. So what does this mean? This would mean that w1 prime of t equals lambda 1 w1. Remember I said we cannot solve this problem in its current form, but we could if the derivative only equaled one term. What have I got now? Each derivative equals exactly one term. Is that a good thing? Yeah, that's a great thing, because what does that mean about w1? Call it c1 e to the lambda 1t, because that's how you solve that differential equation. Now, okay, then what's w2 going to end up being? c2 equal to the lambda 2t, all the way down to wn is cn e to the lambda nt. The c's are arbitrary constants. I cannot know what they are without initial conditions. So I don't worry about that. Without initial conditions, you never know what the arbitrary constants are. They just have to be in there somewhere. Is this a good thing? Yeah, this is a great thing. I've just solved a system of differential equations, but I don't have the y's. So how do I get the y's back again? Where is it? What does y equal? P times w. You've now got w. This is w, by the way. W is all of this stuff. That's the w vector. So how do I get my answer to my original question? I now multiply on the left by p. And now I have the y's. You gotta admit, that's kind of cool. We're going to do a couple problems. It's very abstract, but this here, I don't know who figured that out. I don't know who gets credit for that. It's really not complicated. It's just really, really clever, I think, that someone figured out a way to solve a system of first-order linear differential equations. First order, can't do this for second order. And if it was nonlinear, it won't work because I can't use the matrix algebra on a nonlinear system of equations. But this kind of a problem does come up. And it's considered one of the more important problems in DiffyQ, which is why it's always at the end of the course. In a DiffyQ class, we also consider what if the lambdas are complex. And that problem is really nasty. I'm not even going to talk about that one. When I'm doing this problem we do over the course of 3 classes in DiffyQ. This is 1/2 of one class today in our class because we already know how to do stuff. This problem we actually extend over a few days because we look at all the versions. And it gets pretty ugly. This is one of those I got a lot of pre-printed notes for. It's really hard to keep up when everything's complex and you're doing lots of manipulation. So let's do a problem. Let's solve dy1 dt equals 2y1 plus 3y2, and dy2 dt equals negative y1 plus 6y2. If you thought about this like a system of equations in baby algebra, you'd say, well, can't I just use the addition method, take linear combinations, add them to eliminate stuff? Yeah, but the problem is the derivatives on the left are not scalars. They're functions. In fact, this is not just a function, this is a linear combination of functions. So there's no clever algebra I can perform on this question. I have to change it into this problem. So let me walk you through the process because it's not that complicated in the end. There are some steps involved. So the first thing we want to do is write this as a matrix product. My goal is to diagonalize that matrix. So we'll name it. We're going to call this one the Y prime matrix. We'll call that A, and we'll call that the Y matrix. So obviously those are vectors. Okay. Now I'm going to make, every time you're going to make this substitution, why am I going to make this substitution? Because in the end, when you multiply to get your answer, it's got to come from somewhere. You don't just magically come up with an answer. So you say this. By the way, some of the derivation, let me walk you through it. I'm going to say let that is true. I'm going to start with that. Then in the end, you can say that the y is going to be, sorry, fingers are cramping. How did I leave you with this? Where is it? Y is going to be, right. Oh, I'm sorry, let me just leave it like that. Sorry, I've already got the y equals pw, sorry. With this, I've got this. Let's now diagonalize. So, I've already got enough up here. I'll add stuff if I need it. So a minus lambda I so 12 minus 2 lambda minus 6 lambda plus lambda squared plus 3. That'll be lambda squared minus 8 lambda plus 15. That factors very nicely. So that gives me lambda minus 5, lambda minus 3. And when I set that equal to 0, I get lambda 1 equals 5 and lambda 2 equals 3. Okay? So far so good. Nothing difficult yet. So I'll leave some space over there. So now I have A minus 5 times the identity matrix augmented with zeros. So negative 3, 3, negative 1, 1, 0, 0. So if I multiply the top one by negative a third, and then this adds very nicely. Oops. So I will let x2 equal t, and x1 is also t. So anything of the form t comma t or t times 1, 1. Now, do you want to call your eigenvector a vector or a column matrix? What do you think in this context you want to do?
Aren't you going to make a matrix out of...
I'm going to make a matrix eventually, so a lot of folks would say, let me just call it a column matrix, because then when I check it also, right, you don't multiply a matrix times a vector, you multiply a matrix times a column matrix. So it doesn't matter, but when I do this, choose x1 to be, some of you might say, you know what, it's probably more efficient if I just call it this now. Okay? Now, where's my check? Let me do my check right here. We all know that losing a negative sign. I did everything right, but is it possible I lost a negative there, that one of these should be negative? That's never happened to you, I know. But you know somebody that it's happened to, right? You know at least a couple people that lost a negative and everything fell apart. Well, that's why you check it right now. I easily could have lost a negative in there, and there's no way I could know it unless I check. Oops. And that is 2 plus 3 is 5, negative 1 plus 6 is 5, and that does in fact equal 5 times 1, 1, check. Okay, because my eigenvalue is 5. I always do that, I don't even think twice. Now let's find the second one. So, I'll be negative 1, 3, and then the other one will be negative 1, 3. All right, well that's easy enough. So, which one do I want t to be, x1 or x2? x2. x2 be t, the next one is 3t. So the form will be 3t comma t, or t times 3 comma 1. So I'm going to choose x2 to be 3, 1. And I will check it right here. So 6 plus 3, that's 9. Negative 3 plus 6, that's 3. And that in fact is 3 times 3, 1. All right, so I've got my eigenvalues, I've got my eigenvectors. Can we state our P matrix now? 1, 1, 3, 1. Can we do P inverse? So 1 minus 3 is negative 2, so negative 1/2, so 1, 1, negative 3, negative 1. I gave an exam in my 116 class, and one of the things they had to do is find inverses of, they had to find one 2 by 2 and one 3 by 3 inverse. And I made it so there would be no fractions. And so people went online and found, rather than do row operations, I didn't show them the shortcut. They went online and found rearranging the things in a 2 by 2 would work. So they rearranged things. The problem was they didn't understand, because I did ask a question where the determinant wasn't 1, and all they did was rearrange them, and that's wrong. And then they tried to do it for the 3 by 3, which of course really doesn't work particularly well. I said, what are you doing? Oh, I found this shortcut online. I said, really, did you see it in your textbook? No. In your lecture? No. But you went for online, and they got the shortcut wrong. Therefore, I didn't give them any partial credit, but I thought, why would you go online and look for a shortcut for a 2 by 2? I mean, I did it with nice numbers. I made sure the determinant was negative 1, by the way, not positive 1. So simply rearranging them would not give you the right answer. And I also showed them you check it by multiplying. So not wise particularly. Oh well. I think I'm right. Let me double check. Negative 1/2 plus 3 halves, yes. 3 halves minus 3 halves. Negative 1/2 plus 1/2. 3 halves minus 1/2. So now, what can you say with absolute certainty? I don't actually have to multiply them out. This is what I was trying to maintain to many of you. I know that my eigenvectors are correct because I checked them. I know my P inverse is correct because I just checked it. Therefore, P inverse AP, if this is a quiz, you're all multiplying it out, I know. But if this is an exam where you're being timed, if I know everything I've written so far is correct, do I really have to multiply these out? It would be impossible for this not to be correct. So that's what I'm saying. I wouldn't multiply this out physically. What if these are all 3 by 3s? It takes too long. Plus, you might make a mistake multiplying them out. I have absolute certainty that my eigenvalues, my eigenvectors are correct. And all I did was write them as columns. Okay, so what is this?
5003.
5003. This is the part where I can actually guess. Now, here's the best part of the problem. We started by saying that we did all of this, okay? Now, what did we also show? That I'm going to put this in here. We showed this was P inverse AP W. This was one of the main conclusions that I just showed a little while ago. So how does that help me? dW1 dt dw2 dt is equal to 5003 times w1, w2. All of the work that we did in this problem was to get us to this point, okay? Because from this point to the end should actually be the easy part. We've done all of the linear algebra necessary. Can you tell me what dw1 dt is equal to? Just 5w1. And what's dw2 dt equal to? 3w2. Does everyone see that? I don't need to write them in matrix form. I want to write them in this form. So this implies that W1 equals C1 e to the 5t. I don't need you to do the integration. That's why I started the class by showing you to integrate to find the general form of a population growth problem. You gave you an exponential answer. I want you to just go ahead and write the exponential answer. I don't need you to do the integration, separate it, do all this stuff. I showed you that at the beginning that if this is the question, this is the answer, period. There's no possibility it could be anything different. And that's a tremendous shortcut, isn't it? So am I done with the problem?
No.
I told you what W1 and W2 are, but I don't know what Y1 and Y2 are yet. I've done all the heavy lifting so far, but there's still one more thing. I will put it over here. I'll do it in blue. Y1, Y2 is equal to 3, 1. I'll just be lazy. I'll write W1, W2. So what does Y1 equal? Use the exponential now. I'm just being lazy by not writing the exponentials right here. So W1 was e to the 5t. So this will be C1 e to the 5t plus 3C2 e to the 3t. And what's Y2? C1 e to the 5t plus C2 e to the 3t. And this is the solution to this system. Okay, so far so good? There should be some question somewhere from somebody, eventually. Okay, Steve.
Would we still need these like 3's multiplying these c's?
Okay, good question. If C1 can represent any real number including 0, and C2 can be any real number including C1, then isn't 3C2 just a different arbitrary constant? Yes, it is. Here's the key. Although C2 can be any real number, this coefficient must be exactly 3 times as big as this coefficient. By the way, that is the right question to ask. That is the question that everyone should ask. Why don't I just call this, C3? But then the problem is if I go to check this by taking derivatives, it won't work. I need this coefficient to be 3 times this one, and I need these two coefficients to be exactly the same. So is there a way of checking this after all is said and done? Yeah, the check's actually a piece of cake. What do? Take the derivative of this. Take the derivative of this and compare it to this. So if I said, okay, give me 2 of these plus 3 of these. So 2 of these and 3 of these, that'd be 5 C1Es. And then 2 of these and 3 of these would give me 9 C2Es. And I'm saying that's the derivative of this? Yeah. 5, 9. I mean, you can see it right there. If I actually differentiate, it will check perfectly if I did it correctly. Kind of crazy. Does this problem ever get hard? Well, considering that your eigenvalues are usually, when you're doing these problems, are usually going to be friendly. No, you've already done diagonalization of 3 by 3 matrices, so that's the same problem. The only difference is you're going to go a little bit further. That's the only difference. You got a few more steps after you diagonalize. Our goal on the quiz you just turned in, our goal was to get to here. But you already know this from math classes in general, that when you're solving a math problem, is that always the end of the problem? If it's physics, it might be the first 10% of the problem. When you do a math problem, you've figured out that thing, but that thing is probably used now somewhere else. So we just diagonalized some matrix A. Great, we diagonalized it. Now I need this to answer the question to solve the differential equation. Can't answer it until I do this, because I'll never get this. Oh, but now there's a calculus problem in here that I'm solving, and now I'm taking a linear combination. So in the end, this is the answer. If I gave you initial conditions, you could tell me C1 and C2, but otherwise it's not necessary. Okay? If this is a 3 by 3, it takes a little longer, but it's not harder. The check can be a little messy. I just showed you how to do the check. Literally, take the derivative and compare it to the linear combination on the right. Are they equal? Yes. Then it's correct. Okay? So this is a little bit long. So what I've done on the exam, just so you know, I've given you a 3 by 3 matrix, and I had you diagonalize the matrix, and you did everything. You were done. Now I'm going to give you a system of differential equations. 3 equations in 3, oh my God. And you're going to find you're going to get the exact same coefficient matrix that you've already diagonalized previously, which means you can now say this, and jump to here. In other words, you get to jump to the end of the problem because you already did all the heavy lifting. You don't do the whole problem over again. You take the results you just did, and now, does everybody understand? I'm going to ask you that question, but you're not going to redo the problem. You will have already done the problem. Okay? And then I'm just showing you how can you use that. To have you redo the entire problem from beginning to end, it just takes too long. This is the longest problem of the entire course. This is the longest problem in Math 255, probably. In 255, they rarely do more than 2 variables. But when you do the 3 variable problems, and maybe you have a repeated eigenvalue, and sometimes expressing the answers can be really icky. All right, question? All right, important as an application. In the big picture of things, as you've seen in every chapter, we have really, really cool and important applications of what we just learned. This is considered one of the more important applications of eigenvalues, eigenvectors. I don't do a whole lot with differential equations when I'm doing math at the highest levels, but I do a lot with linear algebra stuff. So the next one I'm going to show you, I think is interesting. Now, I'm biased. I think it's the single most important application problem that exists in all linear algebra, but again, that's just my personal opinion. Don't know all the questions. And that is to basically do an eigenvalue problem on a stochastic matrix. Now, I've been doing research. I've put it on pause for a couple of years. Pre-pandemic, I had a lot of stuff. If you saw the notes that I have typed, it's like the Matrix movie. Just a lot of symbols, hard to follow. But the idea is, if I can take a stochastic matrix and diagonalize it, I might be able to solve a problem that's much easier. And what I'm talking about is something called steady state. So what I'm going to do is go back to chapter 2. Are we back on? Yeah. Okay. There's a problem in chapter 2. I called it the cable company problem. I'm going to restate the problem. And it talks about 2 competing cable companies and then the shotgun shack people. And every year the population shifts. You know, some people stay with their company, they go to the other company, they go to the shotgun shack. Now, this is the lowest level in terms of explanation. Only 2 competing companies and then nobody. Now, think about in real life. Think about commercials you're inundated with. Of course, there's only 1 or maybe 2, I don't know, cell phone companies, right? Or they're like a bazillion of them. Does anyone here not have a cell phone at all? Okay, so you're not the shotgun shack people. But I have met people that don't do cell phones. Usually they're much older than me. Okay, so you're with a cell phone company. How many here have ever switched a cell phone company in your lifetime? Whoa. Somebody didn't raise your hand. I don't think I've ever met a human being in my entire lifetime that hasn't changed at least once. Most people it's about every 3 years on the average, by the way. Why? Because the new company will buy you out of your contract, that kind of stuff. So are people shifting with cable companies, or I'm sorry, with cell phone companies all the time? All the time. So if we made an assumption that the percentage of people that stay with their company or switch to different companies, at least for a short period of time, if that remained fairly constant, and in a lot of situations that is a reasonable assumption, depending on the situation, then not only do you have a stochastic matrix, but you have a situation where you can reach steady state. So in the cable company problem, every person is accounted for. That's why it's a stochastic matrix, because everything always has to add to 1. Right? I can't have percentages add up to something other than 100% if I'm taking care of all the people. And so what we did in that problem was we did repeated matrix multiplication. So I'm going to explain the problem and I'll walk you through it. And then I'm going to show you a very different way of looking at it, which you're going to like. And the thing is, the numbers are not happy, but you do have technology too at times. So you had company A, company B, and then the shotgun shack people, right? No cell phone, no nothing, right? The Amish. Okay. So here, 20% every year went this way, and 15% every year went this way. Here, 10% got fed up and went to none, and the no people said, I want to enter society, and 15% of them went this way. Over here, 5% got fed up, and here 15% went the other way. And finally, who's keeping their own? Well, for A, they kept 70% every year, and B kept 80% every year, and the shotgun shack people, well, if 15% left and 15% left, then how many are they keeping?
70.
Obviously 70%. Yeah. In each case, the percentages have to add up to 100. And so what we have is a situation where if this is repeated year in and year out, we can predict down the road what the percentages with what each group will be. Now, common sense would dictate, hey, the numbers coming in aren't equal. For example, how many are coming into the none? Well, 70%, 5%, 10%. So on a yearly basis of all the people, whatever they have 85% as much next year, don't they? Or at least they have 5% of these and 10% of these. This doesn't add to 100%. They're shrinking. How about this guy? They're losing 10, they're losing 20, but they're gaining 15, so they're basically staying put, aren't they? And what about these guys? Keeping 80, gaining 35, losing 20, they're growing. So in the long run, regardless of what today is, in the long run, who's going to have the most people? B. Who's going to have the fewest? None. Does that make sense to you? That's a common sense approach. They're gaining every year. They're gaining market share. Now, the funny thing is, steady state has nothing to do with what you start with. Now, the closer to steady state you start with, the faster you reach steady state. The steady state is what it is. It's a distribution that is fixed based on these percentages, not based on how many are in each group. Let's say today 100% of the people are in A. Then next year, won't some of them bleed over here and some of them bleed over here? And then we can start the ball rolling. And we will reach steady state regardless. That's crazy. So what we have is what's called a transition matrix. Now, in the textbook, they called it P. I don't want to call it P because our P represents something else. So I'll call it T for transition matrix. And the transition matrix from this picture is going to be 0.70, 0.20, 0.10, 0.15, 0.80, 0.05, 0.15, 0.15, 0.70. And the way we read this is from, I'll put it over here, to. So A, B, no, A, B, no. So if you look at our arrows, 70% of A stayed with A. 20% of A went to B. 10% of A went to no. And what does that first column add up to? In fact, what does each column add up to? 1. That's what makes it a stochastic matrix. Everybody's accounted for. Do the rows add up to 1? No. No, they don't have to. They absolutely do not have to add up to 1. Okay? So this is what's called the transition matrix. So whatever the initial distribution of the population, let's call X 0. The initial distribution of the population. Well, for lack of a better name, A, B, C. All right. A would be the number of people who are with cable company A. B would be the number of people who are with cable company B. And C would be the number of people who are no cable right now when we're starting. So then what will the distribution be in 1 year? Well, it'll be P times X0. Oh, I'm sorry, not P, sorry. Sorry, I called it t. Okay, does everybody agree with that statement? Okay, now it'll be different. That's the distribution 1 year from today. So what's the distribution 2 years from today? Tx1, which is t times tx0 or t squared x0. Ah, Stephen's on something. So what is xn? Does everyone see it's just going to be, you're going to do this? Oh my gosh. When is steady state reached? It's real simple. Steady state is reached. This is true in all stochastic problems. By the way, I do approve that steady state can always be reached in a stochastic matrix. Always. There's no exception. But what if your numbers are, no, as long as your columns add up to 1. Steady state is reached when xn plus 1 equals xn. When next year's population distribution is the same as this year's, we've reached steady state, because that means it's going to stay that way forevermore. Okay, you all with me on that? What's the problem with that? How do you reach that? You have to take a limit as n goes to infinity. Now, will you reach it in a finite period of time? Well, when your count is discrete. People are discrete. That means you can't have decimal people. You'd have to have integer values of people, so you would reach it in a finite period of time. What if this was quantities of water? What if this was measurements? Oh, so I have water in different sources, and every year 70% of the water stays and 20% leaks out into this source. If this were water, steady state would be, yeah, the limit as n goes to infinity, because xn plus 1 will never exactly equal xn, because you'd have decimal values that continue forever. So you see a potential problem there. Plus, the other thing is, as n gets really large, these are only 2 decimal place numbers. They could be 3 or 4 or 5. As n gets really large, what's happening to my storage? I'm storing larger and larger decimals. And of course, all computers have an infinite number of storage when it comes to decimals, right? Or maybe not. In fact, they're going to crap out. They're faster than almost any other type of calculation that exists. They can calculate large numbers. Storing large decimals, that's not really a thing. So although everything I've said is true and correct and we can get there, and in the textbook, I love this, the author gives us some examples. He says, okay, here it is the first 3 years. Now, in 5 years, here's the district. Here's in 10 years. Here's what it is in 15 years. And he's saying, do you see a pattern with the numbers? And if you do, then you can kind of predict it. So here's the thing. It's not the numbers, because this A plus B plus C adds to the number of people in our region. You agree? Now, what if I said, you know what, we've seen through experience that the numbers really do, these numbers really are accurate. That's not an unreasonable assumption. What is an unreasonable assumption? That over the next 10,000 years, the population in our region will never change. Having the stochastic model makes sense. Saying that A plus B plus C will always equal the same number every single year forever doesn't make any sense at all, does it? That's not reasonable in any scenario. So it's not the numbers of A, B, and C, it's actually the ratios, the proportions. Oh, what percentage of the population will be here and here and here? Does that make sense? That's a better answer. Then if I said, oh, if you told me in the end exactly 1/3 of the people end up here, then if I tell you what's the population today, now you can give me a specific number. But the population today won't be the population in 10 years. But if it's 1/3, it'll be 1/3 of that many people in 10 years. So that's a better way to look at the problem. In this example, they overly simplified it, saying the population will never change, literally forever. But because you're taking a limit as n goes to infinity, everything I said is true and correct. So let me look at it a different way. All of this is true. So when is steady state reached? Steady state is reached when xn plus 1, oh, which, by the way, what is xn plus 1? Isn't it t times xn? Isn't that what xn plus 1 is? Isn't that kind of the same? Xn plus 1 equals xn is when steady state is reached. Do you see something here? Let me make it more obvious. Let's put a 1 right there. Do you see something right there? T times xn equals 1 times xn. Means that's not only an eigenvalue-eigenvector problem, the eigenvalue is 1, and the eigenvector is the steady state distribution. Oh. That's why I said it can always be reached. This is one of the simplest ways for me to show it. Every stochastic model can be reached because this is how we do it. So what I need to do, I need to find the eigenvalues for this guy. Okay. Are you excited to find the eigenvalues of a 3 by 3 decimal valued matrix? Joseph isn't, I can tell you. So Joseph said, I have better things to do. Problem is, can't do this one on a computer very well. Because you start getting round off errors and weird things. So I'm going to show you something really cool. I don't know why this isn't in every textbook, but in doing this proof, I realized that trying to work with decimal values on a large scale, I mean n by n, and with no specific number of preset decimal places, the only thing is they have to be the same number of places. As you guys know, anybody in a science class, you can't give answers with different degrees of precision within the same problem. And it's all 2 decimals, or they're all 3 decimals, or they're all 4 decimals. What about sig figs? That doesn't exist in any area of real life except a chemistry class at a college. It can't be significant figures, because then you have decimal places that don't line up. It's always about the same number of decimal places. Sig figs is just a simple way of representing a scientific notation answer. That's not what you actually ever use in real life. Why? Because I give you a 2 decimal place number, and I give you a 5 decimal place number, and you a 20 decimal place number, but I give all to 3 sig figs. You can't work with any of them. They have to all be to the same number of decimal places, not significant figures. That's just for convenience of representation. Nobody uses that in real life. They use computers. They're not rounding any part of the problem ever. That's only a classroom situation. You guys understand it, right? I'm picking on the science people because they make you think that that's how it's done in real life. No, my daughter, the chemist, works with stuff all the time. She laughs. She says nobody in her profession ever even uses the term significant figures. That's not even a term in real life. Outside of a college classroom, it's never used. And you would never get a right answer if you actually did use it. You have computers. You're not rounding anything up. You got everything stored to a point. So what if, boy, it would be so much easier if those were integer values. Man, it'd be so much easier. Let me ask you a question. Okay, ax equals lambda x. Let's suppose. And let's suppose a is icky. Let's suppose a is fractions or decimals. Fractions are just as bad because I could have all these different denominators. You guys have seen that already. With, like, you find an inverse matrix and your determinant was 12. So you have positions that have halves, thirds, fourths, sixths, right? 12s all throughout your matrix. What if I said, but Ka is so much easier to work with? In this case, what would Ka be? Probably 100A, right? Would you agree that Ka might be way easier to work with? So here's the question. What does this equal? Well, wouldn't this be this? Because K is a scalar. We're done. Same eigenvector. If you take a matrix and you multiply it by any scalar, you do not affect the eigenvectors. How do I know? That's it, I just proved it. Do you think that might be useful? Yeah. Means you never have to work with the decimals. But did I preserve the eigenvalue? No. The eigenvalue is now K times as big. You like that? If you take a matrix and you multiply it by any scalar, you preserve the eigenvectors, but you affect the eigenvalues by exactly that scalar. What problem would you rather do? This problem or K times this problem?
Okay.
Yeah. But all we have to be is aware of that it's going to affect the eigenvectors in the end. So if I multiply this by 100, then all my eigenvalues are 100 times what this matrix should be. But my eigenvectors would be the same. And it's the eigenvectors that are actually looking for. In the end, aren't they looking for this vector right here? Oh, but I need the eigenvalue first. And by the way, the eigenvalue is 1. Okay, so let's do it. This problem gets me excited because this is one of the things I started looking at years ago and saying, no, steady state, I see this situation all the time, and I see people just use a computer to raise things to ridiculous powers and round off errors all over the place, and storage, oh my goodness. Wouldn't it be better to come up with the answer before you start the problem? If I said, what will the steady state be? And maybe then I can start my distribution. And I'm going to give you a simple example. You have items that sell on the store. Has anyone here ever worked for a store, like say a big grocery store or something, a large chain? So does everything in the store sell at the exact same rate? No, it's absurd. But for one particular product, there might be multiple brands, and one brand way sells more than the other brands. So do you keep the exact same number of each brand on the shelf at all times? No! The one that sells more, you keep more of. That's just kind of common sense. But how do you know? Well, if you know how things are selling in general, then you always know how to stock them ahead of time. In other words, it really is a steady state issue. Oh, okay, because all I have to do is look at what are the percentage of the turnover. So if I know where to start the problem, then it's much easier to do it this way. They use this, you've heard of Markov chains? This is a version of that. They use this in colleges all the time. If we figure out what percentage of the people are staying for next year, which percentage are leaving, what percentage are graduating, then it helps us for recruiting and incoming class. You see, right now, you're applying, how many have applied to a four-year school in the last couple months? Okay? One of the issues is that four-year school has no idea who's going to be there next year, do they? So what are they basing it on? Previous years and the turnover. But is their college enrollment identical every single year forever? No. But you know what they do like to keep constant? The percentage of freshman, sophomore, junior, senior. They do want to keep that constant because it makes it easier for scheduling purposes, classes, faculty. Okay? If the college is shrinking or growing, they really like it to be at a constant rate for each of those groups. So it's basically this type of problem to figure out what is the steady state in terms of percentages that I can look forward to long term. Why? Because then I know how many applicants to admit next year as a transfer. Well, what's the problem with that? If you're transferring in as a junior, what if no juniors leave? Then you might not get in. Stanford is notorious for it. Stanford is one of the greatest places on planet Earth, and I've had many students over the years apply there and they don't get in. And I've asked Stanford folk, why is it so hard to get in? And they'll say, because no one leaves. Why is it so easy to transfer to UCSD? Because they lose 50% of the freshman class every single year by the end of the second quarter. Every year for 60 years, 50% of the freshman class has failed out. They were on academic probation after the first quarter, failed the second quarter, and kicked out. That's why you can transfer to UCSD in the spring, but not the winter. You haven't failed out yet in the winter. Did you guys know that? That's what, this basically this type of mathematics, so they can perpetually know exactly how many to admit next year, even though they don't know who's coming back. You see, how many applied to UCSD? Do they know how many people are not coming back next year yet? No, they're not even done with the first quarter. But they're using previous years and the percentages because they're saying these percentages really do maintain relative constant. The numbers of people isn't constant every year. Most universities, the number of people they allow to grow slightly. Expansion. Okay? So, let's do this problem. I'm trying to make this, relative so you guys understand this is really a real life problem. So, basically I could multiply t by 100, but there might actually be a smaller number that works also. Notice everything's zeros and fives? Mm-hmm. How about 20? Would 20 be better? Why? You're right. Why is 20 better than 100 as your multiplier?
You're going to have smaller numbers.
Smaller numbers. I'm going to have a characteristic equation that has really big numbers in a few minutes. I'd rather they not be as big. So I'll call it A. Let's let A be 20t. And I want to diagonalize A, not t. It's the A that I'm working on. And so what would that be? 14, 3, 3, 4, 16, 3, 2, 1, 14. Is that look correct? I think I wrote it down correctly. Now, none of the stuff I'm gonna do next is in any textbook, is on any YouTube video, on any website. None of this you're gonna find anywhere else. This is just us, or people that have been in this class. This is stuff I do. A lot, by the way, a significant amount of the stuff I show you is stuff that you won't find anywhere else. It's stuff that I do, my own research. This is one of my pet research projects. I want to find the eigenvalues and eigenvectors of this. And unfortunately, the factorization trick that I showed you is not going to work on this one. But we have a fallback. And we're going to go all the way through this to the end. So let's find A minus lambda I. And you may need your calculators for this one because some of these numbers are kind of large. All right, I'll use the top row. So 14 minus lambda. And I have 224 minus 16 lambda minus 14 lambda plus lambda squared minus 3 times 56 minus 4 lambda minus 6 plus 3 times 4 minus 30, let's see, 32 plus 2 lambda. Did I get that right? God, I don't want any mistakes. Is that correct? Guys, double check for me, please. If we have a mistake, this will not turn out well. And I'll blame all of you. Minus 3, let's see, 56 minus 4, minus 6, 4, minus 3, 2. I think this is correct. Okay. Now, when I simplify the inside here, lambda squared minus 30 lambda plus 221 minus 3 times, and this will be negative 4 lambda plus 50, and this will be plus 3 times 2 lambda minus 28. Aha! So, okay, this is 14 minus lambda. All right, this actually does factor. This is lambda minus 13, lambda minus 17. And this is clearly lambda, 2 times lambda minus 14, and this is negative 4 times lambda minus 12.5. Houston, we have a problem. I don't have any common factors, do I? We got to multiply this out. We got to come up with that. I said it usually works, but it doesn't always work. I've often found the case where if it doesn't work picking a different row or column, you might get lucky. I don't know if this one we actually get lucky. I haven't actually done the other row or column. So I'm just going to just multiply the whole thing out. Oh well. It happens. Okay, you might need your calculators, so let's do it. So 14, all this equals 14 lambda squared minus 420 lambda. What's 14 times 221?
3094.
Okay, good. Lambda cubed plus 30 lambda squared minus 221 lambda. That's just the first term. Well, the next two are really easy though. Plus 12 lambda minus 150 plus 6 lambda minus 84. We good? So far, so good? Yes? Thumbs up? Okay. I'm looking at Rampton because I know he's already got this figured out. He's already got it factored, by the way. All right, so 14 plus 30, negative 420, negative 221, that's negative 641. So then plus 18, so that's negative 623, is that right? Is that right? 18, I think that's right. And then finally, 3094 minus 84 would be, is that the only constant?
Minus 150.
Oh, there we go. So that's 3010, so 2860? Does that look right? Did I screw that up? 3094 minus 234. I think that's correct. Oh, the calculator doesn't work. Oh well. We'll have to do this without a calculator. All right, so all we need to do is use our rational root theorems. Remember how to do it? Plus or minus 1 would be my denominator, and every potential factor plus or minus of 2,860. Actually, no. What do we know is an eigenvalue of the original stochastic matrix? 1. Therefore, what do we know is an eigenvalue of A? 20. We know 20 is an eigenvalue. Therefore, let's do it. How? Synthetic division. I kid you not, this is how you do it. If the numbers were too big, well, not even the numbers too big, if the degree was much higher, what I'm doing is still work. And I'm going to show you that a lot of the work that I'm about to do, I might not even need to do. All right, let's use synthetic division. And that works, so -1, so -20, 24, so that's 480, -143, and then it'll be -2860, and I get 0. Why is that great? That's my remainder. So the negative of what? Lambda squared minus 24 lambda plus 143, which is lambda minus 11, lambda minus 13. Folks, we have our 3 eigenvalues. Crowd as well. I told you there was an out. That was the out. That we knew one of the eigenvalues. And do you see now that factors beautifully?
I thought we were looking for, like, how do we know that one is an eigenvalue?
Because to reach steady state, we said t times the vector had to equal the vector.
Right.
Meaning t times the vector had to equal 1 times the vector. So when you reach steady state, you have an eigenvalue of 1.
And we know that it'll always reach steady state.
Well, that's what I was just showing you. So you're always going to get t. Remember, when xn plus 1 equals xn, but what's xn plus 1? T times xn. So when xn equals t times xn, or when 1 times xn equals t times xn, I have matrix times vector equals 1 times vector. The eigenvalue is 1. So we did it this way because we didn't want to do the decimals. So we knew we were going to get an eigenvalue of 20. So when I used that knowledge, I just factored this. I didn't need technology, did I? Would this work for higher degree? Yeah. And it turns out I'm not that concerned with this part, and I'll show you why in a moment. So we want to use the eigenvalue of 20 because we know we're going to get the same eigenvector no matter what. Everybody agree with that one? We're going to get the eigenvector we want whether we use 20 on A or whether we use eigenvalue of 1 on T. It's going to be the same eigenvector. So let's use 20 on A. It's a little easier. So A minus 20I augmented with zeros. All right. -6, 3, 3. 4, 10, 3. 2, 1. Oops. Sorry. Right. There we go. Yeah, we got that right. 3, 10, 1. Okay. If I multiply this row by...
Shouldn't the middle entry be -4? And shouldn't the...
Oh,
entry
thank
be
you,
negative?
thank you. Oh, well, let's try that again. What did I do? I did something weird. This should be -4.
And then 8 should be -2.
Thank you, Steve. Oh, boy. My eyes got diverted there. All right, let's take the first row and multiply by -1/3. All right, now I have a great pivot. All right, let's take that. So 2 of those, 2 of those, 2 of those. Add those. Hold on a second, something's not right.
The -2 should be a +2.
Oh. Okay. I know that wasn't right. You know why? I wasn't going to get a row of zeros. Good catch. Let me fix that. Oh, that would have been horrible. All right, 2, -1, -1, 0. So -2 of these, -2 of these, -2 of these. There we go. Negative of this, negative of this, the negative of this. Oh, that makes me happy. This is kind of interesting. I don't want fractions. So I'm going to double this row because I really don't want fractions. I'll show you why I did that. This is one of those times when, because the parameterization that's going to ensue may be less obvious. So I would clearly get zeros here, and then when I go hide the negative of this, the negative of this, so if I let x3 be t, then everything's fractional. So what should I let x3 be so as not to get fractions? Say again? If I let x3 be 14, that's still not divisible by 4 though.
4t, right?
Oh, I'm sorry, you said 4t, not 40. I thought you said 14 actually. 4t, will that work? I think that will work. I think that was the right choice. Then what would x2 be? -2 x2 plus 20t, so that would be 10t. And we will check this, obviously. And then x1 would be 7t. Everybody cool with that? So, any vector of the form 7t, 10t, 4t. Now, everything we did is true and correct. I'm going to do an eigenvector, but that's not going to be our steady state vector exactly. And I'll show you why. Because this is supposed to represent percentages or proportions, ratios within. In other words, these kind of have to add to 1, don't they, for me to say that's the steady state ratio? So let's just go this far. So if I choose, I'll call my x1 eigenvalue to be 7, 10, 4. I know every multiple of that works. We already know that. I'll be right here. 7, 10, 4. Okay? So when I multiply that out, 98 plus 30 plus 12 is 140. 28 plus 160 plus 12, that's exactly 200. 14 plus 10 plus 56, that's exactly 80. And that is exactly 20 times 7, 10, 4, isn't it? So we found the eigenvector in terms of ratios. So think of it another way. In terms of population, for every 4 people in region 3, there are 10 people in region 2, there are 7 people in region 1. So if I wanted the actual steady state ratio, 7 plus 10 plus 4 adds to 21. So if I said the steady state vector, what would it be? 7 over 21, 10 over 21, 4 over 21. Now, if I said, all right, there's 1 million people in the area, there's 150 people in the area, there's 10,000 people in the area, then I just multiply each of those by the population of the area. That's it. Okay? Everything we did was necessary, but maybe there's stuff here that's extraneous. Let's find one other eigenvector. I want to show you something. Yeah.
Why over 21 again?
Because 7 plus 10 plus 4 adds up to 21.
Okay.
And I need those 3 numbers add up to 1, really.
So if we knew that one of the eigenvectors was going to be 1, or
Values,
in this case
eigenvalues.
20, or sorry, eigenvalues, why did we find the other 2?
Well, to make sure that we actually, what if I messed up and this didn't factor at all? What if I use the 20 and it didn't factor? Then it means I've made a mistake in my setup. Why does that matter? I already know the 20, but then it means the eigenvector might have also been. It wouldn't mean that I messed up something. So I factored it just to make sure that I didn't make a mistake. Now I'm going to keep going and show you that maybe
Okay.
even that was unnecessary. That was a great error check, that 20 worked and I got numbers. Let's do the 11. All right, let's do a minus 11I. I gotta go fast, I gotta get to class in a few minutes. So if I do minus 11, I'm gonna have 3, 3, 3, minus 11, so 4, 5, 3, minus 11, so 2, 1, 3. Oh, this should be easy. So if I multiply row 1 by a third, all right, negative 4 of those, negative 4 of those, negative 4 of those, negative 2 of those, negative 2 of those, negative 2 of those. Wow, this one looks easy, doesn't it? Why don't we just start with this one? Shoot. So that's 0, 0, 0, 0, and when I go that way, it's going to be 1, 0, 2, 0. Beautiful. So, if I let x3 be t, then x2 is t, and then x1 is negative 2t. So any vector of the form negative 2t, t, t, or t times negative 2, 1, 1. So my second eigenvector clearly is going to be negative 2, 1, 1, which for the rest of our lives is utterly worthless. Why? Everything we said is correct. That is the eigenvector that goes with the eigenvalue of 11. This is a population distribution. Can't have opposite signs. So in other words, the steady state eigenvector was the one that went with the eigenvalue of 20 for the adjusted matrix, eigenvalue of 1 for the original matrix. I got two other eigenvector values, and each of them will have eigenvectors. But in both the eigenvectors, I'm going to have numbers with opposite signs, which normally isn't a big deal, except this is supposed to represent a population distribution. So do you agree that's an impossible distribution? Which is why they are not steady state vectors. They will work for solving the problem. If I multiply by that vector up there, I will get 11 times the vector, and everything worked out perfectly. But it can't be a steady state vector because it's supposed to be a population distribution. I have to have 3 positive numbers. I can't even have a 0 in there. So going back to Matthew's question, which was the right question, if I know everything is correct, did I even need to deal with the rest of this problem in actuality? No, I didn't. Did I need to find any other eigenvectors? No, I don't. That's why I'm showing you right there. I found the eigenvector that went with the right eigenvalue. How did I know 20 was the right one? Because we took 20 times t originally, so we know we multiplied the eigenvalue by 20, but we did not mess with the eigenvector. That's what I was proving earlier. I said, I think that is actually a really important thing. It's not any kind of a theorem, and you won't find that in any textbook. I've never seen it. And I've had a lot of linear algebra classes. I've never seen any of this in any class I ever took, just so you know. I've never even seen the questions asked. But I think this is a really important question, because reaching steady state, Markov chains are one of the most common things you deal with in real life, high-level mathematical stuff. And finding steady state actually can be really important. There's a great question in the homework. They call it the rabbit problem. And I'm just going to read it to you. I'm not going to do it. We got to go soon. But the problem, you have a rabbit store, and you're trying to figure out how many rabbits of each age should you stock in your store. Because you don't want to sell all the rabbits of one age and then run out in different ages and so on. You got to find a problem now. Sorry, where is it? Oh, okay, they asked the question in a different format. Okay, the previous edition. They said, in the first year, rabbits don't have any offspring. In the second year, rabbits tend to have, and they give you a number of offspring. And in the third year, they tend to have these many offspring, but they don't live to a fourth year. So how many should you stock to make sure you always have the same proportion of rabbits? It's a really interesting problem. If all I have are first-year rabbits, then next year I have nothing but second-year rabbits because they didn't have any offspring. If all I have are third-year rabbits, then next year they all have babies, but they're all dead. I want to have some of each, but it's an eigenvalue, eigenvector problem to reach the steady state of the ratio of rabbits I need. Why? Because the population of rabbits is going to grow rapidly. But I don't want it to get distorted. That's the same as the items on the shelf at the store. I don't want it distorted. I want the ratio of items to remain the same in terms of based on the sales. That's what steady state is all about. And it's a real practical everyday problem. Kind of cool. All right, can we stop?